Aha, here we are again. After talking about this sort of abstract four-step hypothesis testing process, last slide, excuse me, for the situation where we know what that population standard deviation, what that sigma is. We're now getting ready to go through some examples, three examples, and we're going to go through them in beautiful, wonderful, excruciating computational detail. We're going to do not just the computations and calculations, we'll talk as well about the meanings, the interpretations, and the implications along the way. This should reinforce the theory that we absorbed previous to this. And again, I would encourage you, after going through the slide, um, revisit the old slide, do a lot of practice problems, and then keep going back and forth between these things. This is a really important foundational topic, so it's really worth committing some time to knowing it well. All right, so our first example, it's actually an example that we've seen before. So the three examples in this PowerPoint are the three examples we looked at earlier when we very first started talking about hypothesis testing. So as you might remember, in this particular example, we were secret FDA agents, and we have been getting a lot of complaints about McDonald's and their Big Macs. We looked into it. Big Macs are alleged to have 30 grams of fat. We wanted to test whether or not that mean fat content might in fact be larger. So as we've already talked about, we would need to start this process by taking a sample. Let's say that we have enough time and resources, man and woman power, to go out and actually collect 150 Big Macs. So we do that. We look at the sample mean and we find it's 33 grams of fat, a bit more than 30. Now everyone, of course, except for maybe people that go to Burger King, know that the population standard deviation of fat content is 10 grams. Maybe also people who go to Chick-fil-A. Now let's go ahead and test the claim. Let's test our claim at the 0.05 significance level. I don't think that I've used this language before. We have certainly talked about that alpha. Alpha is also sometimes referred to as the level or significance level of a test. So when I say let's test this at the 0.05 significance level, that's just saying let's for step 4, let's use an alpha of 0.05. So, step 1. Step 1 is set up our hypotheses. We did this in the previous PowerPoint. These are the hypotheses, right? So our alternative hypothesis is that the mean mu is greater than 30. Step 2, construct our test statistic. The formula for the test statistic is x bar minus mu naught divided by sigma over the square root of n. All those numbers are embedded in the previous word problem. Our sample mean was 33, our hypothesized mean was 30, our standard deviation we were told is 10, and we took a sample of 150 Big Macs. Now, I strongly encourage you to do this calculation yourself. You have fractions within fractions. It is easy to get the order of operation wrong on your calculator. You do not want to be doing this for the first time on a test or even a quiz. Do it now. And if you cannot get that 3.67, come talk to me about it. The fact that this is 3.67 means what? It means that the sample mean, right, is 3.67 standard deviations above the hypothesized mean, right? I could also, without this formula, I could have observed that the sample mean is 3 grams of fat more than the hypothesized mean, right? 33 is 3 above 30. But units of grams of fat are not meaningful to us as researchers. What is meaningful is units of standard deviation. So by seeing, right, that the difference is 3.6 standard deviations, 3.67, we could say that's a lot, right? Remember, we know that really 2 standard deviations away from something is a fairly large distance. 3 is tremendously large. Remember, 99.7% of the time you're within 3 standard deviations. This is more than 3 standard deviations above the mean, which is a large difference, which means that it's probably unlikely that something like this would have occurred. Let's verify that further by looking at our p-value. Our p-value is the probability that z is greater than z test, right? That greater than matches up with the greater than 30 in my alternative hypothesis. So this is the probability that z is greater than my test statistic 3.67. Now I didn't draw the pictures. By now I should have perfected the skill, and it should be fairly obvious to me that to find this probability, right, z is just a normal distribution with a mean of 0 and a standard deviation of 1. So finding this probability is just normal CDF. My lower bound is 3.67. In theory, there is no upper bound, so I do that 1 gajillion. 1 times e to the 99, 0, 1. I do that, I get 0.000121. What does that number tell me? It tells me that if the null hypothesis was true, if Big Macs really did have 30 grams of fat on average, then there is only a 0.01% chance that we would select a sample of 150 Big Macs that had a sample mean of 33 or larger. Right? We're saying that, yeah, if McDonald's Big Macs really had 30 grams of fat on average, it is technically possible that I could take a flukish sample, that I could take a exceptionally flukish sample that has 33 grams of fat, that I just maybe, just by horrible luck, could pick like the 150 fattiest Big Macs in the country. But even though technically it's possible, it's extremely unlikely. It's a 0.01%, 1/100th of a percent chance that that would happen. And so what's more likely then? That the whole premise that we base this calculation on, the whole fact that McDonald's Big Macs have 30 grams of fat on average, right, is cast in doubt.
So, step 4, we take our p-value, what we found in step 3, 0.000121, hey, like math 121, and we compare that to our significance level, to our alpha. In this case, we were told way back at the beginning that we should be using 0.05. When the p-value is smaller than alpha, we reject the null hypothesis. That is always true for any type of hypothesis test. You need to know that. You need to learn it. You need to love it, or at least you have to fake that you're loving it. It is probably the most pivotal part, again, the most important part of all hypothesis testing. That is, walk around your house, walk to the car, drive your car, ride the bus, sit on the toilet, just constantly be saying to yourself, when the p-value is less than alpha, we reject the null hypothesis. When the p-value is more than alpha, we fail to reject the null hypothesis. In this case, it's less. As we just memorized, that means we reject the null hypothesis. Put in the context of the problem, always an important step, we would say at the 0.05 significance level, there is enough evidence to conclude that that mean fat content in a Big Mac is more than 30 grams of fat. When we're putting it in the context of the problem, we're always really looking at that alternative hypothesis. That's the claim that we're trying to make, or the claim that we're investigating. And we're always basically saying that there is or is not enough evidence to sort of substantiate that claim. In this case, small p-value indicates that there is a strong amount of evidence. So we would ultimately say that McDonald's is lying, your words, not mine. And as a government watchdog agency, maybe we would force them to relabel their Big Mac nutritional information.
Example 2. Again, this and the next example, these are both examples taken from the first PowerPoint. I'm just adding a little bit of extra information onto them. So it's the ACT writing example where a test preparation course is claiming that students who take the course will finish faster on average than the 240 minutes that people who don't take the prep course finish. So, if we wanted to test its claim, we could enroll 50 students in the program. Let's say that we do that. And let's say that they finish with a sample mean of 234 minutes. This is technically less than 240. However, is it so much less than it that we feel that it's sort of above and beyond any doubt is indicative that all students on this test prep thing will finish on average less than 240. Well, to do that, or to decide that, we're going to need to do a hypothesis test. To do our hypothesis test, we need to know what the population standard deviation is. So let's say that it's 30 minutes. And then let's go ahead and use this information to test the claim at that 0.05 level, using an alpha of 0.05, an alpha of 5%. Step 1, right? This is a it seems like a lot at first, but it's very repetitive, right? It's like what? It's like ballroom dancing. Step 1, step 2, step 3, step 4. Step 1, step 2, step 3, step 4. And when you first started, it's a little overwhelming, right? But as you do it more, as you sort of abandon yourself, right, to the pattern, then you'll find that the statistics just sort of takes over, and then it becomes almost second nature. So step 1, set up our hypotheses. These are the same hypotheses as before. Our alternative hypothesis is that the mean, mu, the average time to test completion, is less than 240. Our test statistic, right, x bar minus mu naught over sigma over the square root of n. Plug in all the numbers, I get negative 1.41. Again, you shouldn't just look at these things. You should be pausing the PowerPoints. You should be pulling out your calculator, your pen, your paper. You should be verifying all this. I get negative 1.41. The negative means, right, that it's below the hypothesized mean. The 1.41 means that the sample mean is 1.41 standard deviations below the hypothesized mean. The p-value, the probability that z is less than z test, right? Less than because of the alternative hypothesis. The alternative hypothesis was that mu was less than 240, so my p-value is going to be the probability that z is less than the test statistic. That is, the probability z is less than negative 1.41. Again, z is just a normal random variable, mean of 0, standard deviation of 1. So I could find that probability using normal CDF. Since it's a less than problem, I do negative 1 E99, comma, negative 1.4101. If I do that, I get 0.0793. That's my p-value. How do I interpret it? I interpret it as this. Even if the students had not taken the test prep course, right, which essentially is equivalent to the null hypothesis, right? Even if their average time to completion is 240 minutes. There would still be a 7.93% chance that a sample of 50 students would finish on average, would have a sample mean of 234 minutes or less. To make our decision, we take that p-value, the 0.0793, we compare it to our alpha, our 0.05. In this case, the p-value is more than alpha. Any time for any hypothesis test, does not matter how the alternative is set up. Any time the p-value is more than alpha, we fail to reject the null hypothesis. At the 0.05 significance level, there is not enough evidence to conclude that the mean time to test completion is less than 240 minutes, right? Put a little bit more simply, we do not believe the course is effective. Yeah, not shabby, right? It's pretty cool to be able to use statistics and statistical reasoning, all the things that we've spent the last however many weeks or months talking through, right, to good use. Last example. So a healthy systolic blood pressure is known to be 115. Group of patients could be unhealthy if it's more or less than that. So let's say that we happen to have 100 patients on a particular medication. And maybe we want to what? We want to test to see whether that medication has adverse side effects with respect to blood pressure. But we'd be interested in determining if the medication's giving them elevated blood pressure or depressed blood pressure. So let's say that we have our sample of 100 patients. We look at their blood pressure and we find the sample mean blood pressure for a sample is 116, which is a little bit elevated. Is it enough above 115 for us to be worried? Well, to answer that question, you need to know the population standard deviation. So let's say that's 12. And just to mix things up a little bit, let's test whether or not their blood pressure is sort of unhealthy, whether or not their blood pressure is different than 115. Let's do it at the 0.10 significance level, just to show that 0.05 is not entirely scripture. That you can do other comparisons or other significance level tests. So step one, set up our hypotheses. Just like before, the mean is not equal to 115 as our alternative, right? The null is always a statement of equality, so it's that the mean is equal to 115. Step 2, where's my test statistic? Same formula, always the same formula. X bar minus mu naught, sample mean minus the hypothesized mean over sigma over the square root of n. Plug all those numbers into the formula, I get 0.83. So what does that mean? It means that the sample mean is 0.83 standard deviations. I'm sorry, that's some bad cut and pasting. The sample mean is 0.83 standard deviations above the hypothesized mean. Sorry about that. Above because it's a positive number. Step 3, where's my p-value? Remember, for case 3, for not equal to, we had a slightly more complex formula for the p-value. And actually, oh man, I feel really bad. I'm sorry. The p-value is actually 2 times the probability that z is greater than z-tests. That's what I get for writing these PowerPoints after I take a nap. It's 2 times the probability that z is greater than, not less than, I apologize, greater than the absolute value of z-test. That's 2 times the probability that z is greater than 0.83. So I did put the correct normal CDF formula in there. That's 2 times normal CDF. My lower bound should be 0.83. In theory, there is no upper bound, so I put 1E99, mean of 0, standard deviation of 1. So I get 2 times 0.2033. I get a very large p-value of 0.4066. Which is basically saying what? It's saying that if patients on this medicine really did have a true average blood pressure, a true mean, mu, of 115, then there's a 40.66% chance, that is, it's not particularly rare or uncommon, that a sample of 100 patients would have a sample mean that's 1 millimeter of mercury away from 115 or further. Right, because remember, the sample mean was 116, and that's of course 1 millimeter away from 115. We can then take this p-value to ultimately make our decision or our conclusion. The p-value is 0.4066. That's greater than or larger than 0.10, which is our alpha level. Anytime the p-value is greater than alpha, we fail to reject the null hypothesis. We would say at the 0.10 significance level, there is not enough evidence to conclude that the mean blood pressure for patients on this medicine is different than 115, right? So we would basically be concluding we do not think that our medicine has any adverse side effects with respect to blood pressure, at least. Patients on this medicine seem to have a healthy blood pressure.
It's very easy to do this in our calculator. Pretty similar, pretty much identical to what we've already learned how to do for confidence intervals. We hit stat, of course we do, it's stats class. We go to tests, certainly would be useful on a test. We go to z-test. Now, I think actually the cursor might start on z-test, so you might not actually have to go uptown or downtown. You might just, you know, where you are, that's where you are. So select z-test, fill in the relevant information, go to calculate, hit enter, and you should be good to go.
So here I am using the calculator to do example 3. Here's what it looks like. So that mu naught, remember, is our hypothesized mean. So I filled that in. This is the information from example 3. I filled in 115. The sigma, the known population standard deviation, well, we were told that was 12. The sample mean is 116. Sample size was 100. So the second to the last line, that's where I specify, right, which of the three alternative hypotheses I'm using. In this case, we used the not equal to alternative hypothesis. It was that case 3. So my cursor has selected that leftmost option, the not equal to mu naught. I would then put my cursor over calculate. I would hit enter. And so here it is, right? It tells me on the top line mu is not equal to 115, so it tells me the alternative hypothesis that it used. The second line is our step 2, which is our test statistic. The test statistic is 0.833 repeating. The p is the p-value, so the p-value is 0.4046. That's a little different, I think, than the one we got. What was ours? 0.4066, mainly because I rounded that 0.8333333 to 0.83. The sample mean is 116. The sample size is 100. So it's a little bit easier. It's actually a little bit more accurate. I have a more accurate p-value. Notice, I still need to do the step 1 on my own, because setting up that hypothesis is something that I need to do, right? Because I have to actually tell the calculator what the alternative hypothesis is. However, once I've done step 1, the calculator does steps 2 and 3 for me. It gives me the test statistic, gives me the p-value. I then still need to take that p-value, and I need to do step 4 on my own. I need to compare it to my alpha or significance level on my own. The calculator will not do that for me. So, the calculator does step 2 and 3, takes half the steps off my hand. It's not too bad. It's a nice collaborative relationship between us and our calculator.